In this short lecture clip, we will look at the main definitions and concepts in probability theory. To do this, we will highlight these concepts using one of the simplest distributions in probability, which is the Bernoulli distribution. So in this lecture, we will outline some of the key topics in probability, highlighting it through the example of the Bernoulli experiment. So the first half of the lecture, we'll look at some main key concepts. When we look at just modelling what's known as a univariate random variable, when we just look at one particular event occurring or not, whether someone has a job or not, say. We then extend all these concepts looking at when we have more than one variable. So we have multivariate analysis, where we, for example, may want to model the probability that someone has a job and whether or not they've got a degree, and so on. Okay, so we'll look at the notion of a density function, the cumulative density function, taking expectations or the average of some variable, working out the moments, the mean and the variance. We'll look at the notion of a joint distribution and the marginal distribution, and also importantly looking at the properties of a conditional distribution. So these are some of the key topics which you will see in any statistics course, and again we use the Bernoulli example because it's very simple and it highlights these definitions clearly. We'll begin by defining what is a Bernoulli experiment, and then two key concepts in probability, the notion of a sample space and a random variable. So the Bernoulli experiment is very simple. It's some random outcome where an event occurs or it doesn't occur. So for example, whether someone's employed or they're not employed, whether it rains or it doesn't rain. So the sample space is literally every possible outcome of the experiment. So we often use the notation omega, and in this case it's a set which taking the employed example, they're either employed or they're not employed. So the sample space, more generally, is every possible outcome of the experiment, and we are just focusing in just on the Bernoulli experiment. But again, this notion generalizes. So a random variable then, call it x, is some variable which assigns to every point in the sample space a number. So in here, for example, we could attach the number 1 if they're employed, and we could attach a 0 if they're not employed. A random variable in general just attaches a unique number to every point in the sample space. So again, we could attach 4 and 5, or -1 and -2, and so on. The benefit of the random variable, the reason why we look at this, is because when we look at modelling the properties of variables with uncertain outcomes, it's difficult to generate general mathematical formulas as a function of whether someone's employed or not employed, whether you get a head or a tail, and so on. So when we look at modelling the probability that these events occur, it's much more convenient to work with functions of a number. So this is why we work with a random variable. So overall, the random variable assigns a number to each outcome. So from now on, when we look at the probability x equals 1, all we're saying is what's the probability that the person is employed. As you can see, it's much simpler to work in this general setting where we work with the probability some variable takes a number, as opposed to working more abstractly with the probability someone's employed. We will now move on to define another key concept in probability, the notion of a probability density function. Again, we'll highlight this for the Bernoulli experiment, which is it's a very simple discrete variable. So a discrete variable is a variable with a finite number of distinct possible outcomes. So in our case, we had a variable where x equals 1 or not. More generally, discrete variable could take on many numbers, 0, 1, 2, 3, 4, 5, and so on. Okay. So the definition, which we call little f of x, is that literally f of x, a PDF, is a probability that our random variable takes on any particular value, little x. So capital X is the random variable, and little x is just some possible outcome. So it's just some outcome. And again, we evaluate this function at every possible outcome. So the density function then just gives you the amount of probability of every possible outcome. So for the Bernoulli random variable, give the details again given at the bottom of the screen, we can see it's very simple. X equals 1 with probability just x equals 1, which we can call P. And we have then probability that x equals 0, the only other possible outcome, with probability x equals 1 minus p. And the two probabilities have to sum to 1, because this is every possible outcome. The Bernoulli Random Variable doesn't take any other outcomes. So in this case, the PDF is very simple. F of x, the PDF for Bernoulli, is just p when x equals 1, 1 minus p when x equals 0, and the probability is 0 for every other x. So we call it every other possibility. So this is it. This gives you, we can draw this also in a diagram. It gives you the probability that this Bernoulli variable takes on every possible value. So again, we could draw this. So we could, let's just take the case where we have, let's say a third probability the event doesn't happen, and 2/3 chance that it does. So we have, this is a probability, this is event 1 or not, this is 1. And again, every other possible outcome doesn't occur. There's 0 probability here. So again, the probability x equals 1 could be a third, 2/3, the event happens, and a third, the event doesn't happen. And so on. This is just one particular example. For every different p and 1 minus p, we'll get a different PDF. So this is just a visual plot of the probability density function. It just gives the density or the amount of probability at every possible outcome. And again, this generalizes if we had a variable which took on values 0, 1, 2, 3, 4, 5, say, which have a probability that x took every possible value. Again, we can work out its function. This gives us all the information about the outcome of x, the probability. From the probability density function, we can derive what is known as a cumulative density function, another key concept in probability. The cumulative density function, sometimes known as a distribution function, just gives us a probability the random variable is less than some particular number. So the definition, CDF, is just probability the random variable x is less than or equal to some particular outcome, little x. And we use capital F of x as notation. So for example, if x were income, then the distribution function at, say, $25,000 would give us the probability income was less than or equal to $25,000, and so on. For the Bernoulli random variable, the PDF, capital Fx, is very simple to derive because x only takes a limited number of values. If we evaluate the function at x equals 0, well, the probability that x equals 0 is just equal to the probability x equals 0 because x doesn't take any other value under 0. It takes the value 0. The probability x equals -1 and so on are all equal to 0. So at x equals 1, it's just the probability x equals 0, which is just 1 minus p. Then evaluate the function at 1. Well, the probability x is less than or equal to 1 is just the probability x is 1 plus probability x equals 0. All other outcomes have a 0 probability. Well, this is just 1 minus p plus p. Well, this will be p plus 1 minus p, which is just 1, because that exhausts every possible outcome. Again, evaluating any x greater than 1, we get 1, because the probability x is less than or equal to 2, 3, 4, 5 is just 1, because every possible outcome is within there. If we evaluate the function any x less than 0, again, we will get 0, because it doesn't take any value less than 0. So again, we can draw this in a diagram. We can see it's very simple for the case of a Bernoulli random variable. The cumulative density function is very simple. We just literally add up all the elements from the... So again, at x equals 0, we have p, and then at x equals 1, it will just be 1. So again, this would be 1 minus p, and this would be 1 here. The probability at 0 and 1. So it's very simple here. The probability x is less than or equal to 0, well, it's just the value, probability x equals 0, 1 minus p. And x less than or equal to 1 is every possible value. So this would just take value 1. And this is it. And then from there on in, it'll be also 1 all the way onwards as well. Because the probability x is less than 2, 3, 4 is again just all 1. And again, it's equal to 0 for any value less than 0. We'll now move on to define the expectation operator and the moments of a distribution, especially the mean and the variance. So the expectation operator E performs an operation on some entity. So E of g of x, and g is just any arbitrary function. So for example, we could just have g of x equal x, or g of x equal x squared, and so on. It's just defined, well, is a sum across every possible value x takes of the value of the function g of x at that point, little x, multiplied by the probability that x took that value. So you can see it takes an average. The expectation gives a measure of centrality. It gives a measure of the average value of this function of x. Okay. It becomes clearer when we take the simple example of a Bernoulli random variable. So in this case, we want to look at the mean. So the mean is, the definition is just e of x. So this is just a case of g of x equal x. Well, general definition, sum across every value x takes of the x times the probability that we observe that particular outcome. So it's very simple for a Bernoulli because x takes two values. So it equals naught times probability x equals naught, which is just 1 minus p, plus 1 times the probability x equals 1, which is p. All the other x's have probability naught. So this just equals p. So the average value of x for a Bernoulli random variable is just the probability that the event occurs. We can then work out the variance. So remember the formula for the variance of x, the general formula is expectation, or the average of x, the deviation of x from its mean, all squared. So it gives a measure of the volatility or the variability of some random variable. So we just worked out e of x before, it's p, so we can simplify down. This is the expectation or the average, e of x minus p squared. And again, we just apply the formula now at g of x equal x minus p. So now we have, this is the formula, we can plug it in to the general definition and go from there. So we have then, it's just equal to sum of all values x takes of x minus p squared. Note little x is the value, different values x takes, capital X is the random variable. So we have little x minus p squared times by the probability to observe that particular outcome, little x. And again, this simplifies because we have two possible outcomes, x equals naught, so we get minus p squared, times by 1 minus p, which is a probability, x equals naught, plus x equals 1, we get 1 minus p squared, and the probability that we observe, x equals 1, is p. So we can then simplify. The minus drops out because it's squared, so we just get p squared 1 minus p. So we can take outside the bracket p 1 minus p, which will leave us p here and 1 minus p here, which sums to 1. Inside the bracket sums to 1. So we have the variance of a Bernoulli random variable is p times 1 minus p. So again, the expectation just takes the average of some function of x with respect to the distribution of that particular variable. And we highlighted this for the Bernoulli case. Up until now, we've looked at modelling the probability of just one random variable. We looked at the Bernoulli random variable where an event occurs or it doesn't occur. More generally, we may want to look at studying the probability of multiple events occurring. So we may have whether it rains or not tomorrow, and whether or not there's a financial crash tomorrow, and so on. So take the case, to highlight this, take the case of a bivariate random variable. So the case where we just have two random variables. We can have the random variable x, which takes again value 1 and naught, the event occurs or it doesn't occur. So for example, x could be whether someone is employed or not. And let y, again, another random variable, this could be whether someone has a degree or not. So we may want to look at the relationship between having a degree and being employed, and so on. So in reality, we can think of many different examples where we have more than one random variable. And again, everything generalizes to 3, 4, 5, 6 random variables. And again, we're just going to focus on the Bernoulli random variable, which is a discrete variable. So the definition is simplified. So we use the notation fxy to denote, it's just notation for the joint distribution of x and y. Well, it's just a probability that x takes on some particular value little x, and that the random variable y takes on the particular value little y. So again, x and y are random variables, and little x and little y are just particular outcomes. And again, it's a function. For every possible pair of outcomes, we will get a different probability. So here we can define a new sample space. So in this world, There's 4 possible outcomes. X occurs, Y doesn't, Y occurs, X occurs, Y doesn't occur, and so on. So we can have 1 and not, 1 and 1, not and 1, and not and not. It's all 4 possible outcomes. If we observe X and Y together, whether someone, say, has a degree or not, and whether or not they have a job, then there's 4 possible outcomes. This would be the new sample space. From here on in, all the concepts of probability are the same. We can visualize this by drawing it in a plot. So again, X takes 2 values, 0 and 1. Y takes 2 values, 0 and 1. And again, we just give an example. Each element in each square is a probability. This is a 0.4 is a probability X equals 0, Y equals 0. 0.1 is a probability Y equals 0, X equals 1. 0.3, probability Y equals 1 and X equals 0, and so on. So this just gives us a visual plot of the joint density function. The probability that X and Y take on every possible combination of values. So for example, F, the joint distribution at 0 and 1, well, it's just probability X equals 0 and Y equals 1, which would just be 0.3. So again, you could write out the function. It'll take on 4 values, the probability of every possible event. And again, it's the probability of every possible event in the sample space. There's 4 possible events in the sample space. 1, 2, 3, 4. They all have a certain probability. And again, they must all sum to 1. So it may be that we have information on the joint distribution. We know the probability that X and Y takes every possible distinct combination. But from this information, we may want to work out, well, what's just a probability that, say, X takes on a certain value, or that Y takes on a certain value. We may be interested in what is their individual distribution of each possible variable. So again, the marginal density of X, with definition, little f of X to denote, it's the marginal density of X. It's just defined as a probability that X takes on every possible outcome, little x. And to get this, we just sum the joint PDF over Y. And to see why this is, take an example in the lower left corner. If we wanted to work out what is the probability X equals 0, well, X equals 0 can happen with 2 possible values of Y. We don't care about the values of Y. X can equal 0 when Y equals 0 with probability 0.4, or X can equal 0 and Y equals 1. So if we add them together, this gives us the probability that X equals 0. And the same for X. So again, we just have probability X equals 0, Y equals 0, plus probability X equals 0, Y equals 1. We have just summed across, we just summed the joint density across every value of Y. Similarly, if we want, here's the probability X equals 1, well again, X equals 1 here, and X equals 1 here, which is 0.1 plus 0.2. So this would give us, if we sum the columns, it would give us the marginal density. And again, these probabilities sum to 1. So again, the probability X equals 1 is just a probability X equals 1, Y equals 0, plus probability X equals 1 and Y equals 1. We can do the exact same thing then for the marginal density of Y. The marginal density of Y is just the probability that Y individually takes on any possible outcome. To get this, we just sum the joint density of Y and X across X. So going now to Y, looking at the table, well, there's again Y equals 0, well, with 0.4 and 0.1, we get 0.5, and Y equals 1, well, it happens here, and it happens here, with again probability 0.5. Again, they sum to 1. So earlier we defined the moment of just one random variable X. Again, we can generalize the notion of a moment to the case where we have a joint distribution. So the expectation of some function of X and Y, G can be any arbitrary function, for example, G of XY just equals X. Well, it's just every possible value the function takes at each outcome X and Y, multiplied by the probability to observe the X and Y. Then we just sum across every possible value of X and Y. This gives us a measure of the average value of this particular function of X and Y. It's every possible value the function takes for every possible combination of X and Y, multiplied by the probability that each outcome occurs. So we can use this general definition to work out what's E of X. using the joint distribution function in our example here? Well, we have the general formula, sum across x, sum across y, of plugging x into this formula here, times probability x equals x, y equals y. Well, what's going to happen here? We can see, obviously, x doesn't depend upon y, so we can take x outside here. So we can rewrite this sum x over x times of sum y of probability x equals x, y equals y. Well, what is this here? This is just, by definition, is the marginal density of x. We've just summed the joint density across y. So we can see this is just sum x times probability x equals each particular part of x. So it's just the e of x formula from before, which you can work out from the information here. We have the joint density fxx. Remember, it's just a probability x takes every possible value here, which we worked out before. So x takes two values. X takes 0 with probability 0.7, and x takes 1 with probability 0.3. So we have the average value of x is 0.3. We can now do the same thing for the mean of y. Again, plug y into the formula above, e of y. Well, sum x, sum y, every possible value of y times this, the joint density. Again, this sum can come inside here because y doesn't depend upon x, so we can rewrite this like this. And again, we can see the similar thing can happen to before. We can see this term is just the joint density summed across x, which by definition is just the marginal distribution of y, times probability y equals y. And again, we have the joint density for y here. This is just fy, y. So we have 0 times 0.5, so probability y equals 0, plus 1 again times 0.5. So we have 0.5. Okay, so more interestingly then, we take this, we want to work out the average value of this particular function here. So we can see this here, e of the average value of x minus its mean times y minus its mean. We know that this is just defined as what's called the covariance of x and y. So this is the proper definition of the covariance of x and y. It gives a measure of how x and y move together. So we can see it takes e, the average of the deviation of x from its mean, times the deviation of y from its mean. So we can see, for example, when x is bigger than its mean, if x is bigger than its mean on average, and y is bigger than its mean on average, then we'd expect this to be bigger than 0. So that would give a measure that they both move together. If x was less than its mean, which would give this less than 0, and y was less than its mean, and together, on average, again, this would be on average greater than 0. So if they both move together, we'd get a covariance that was bigger than 0. And likewise, if they moved in opposite directions, if when x was lower than its mean, so we'd have this less than 0, and when y is bigger than its mean, again, on average, this would be less than 0, which would give us a measure that they both move in the opposite direction. So this is just a bit of intuition of what the covariance does, but we can work this out just applying this definition. We worked out e of x and e of y from before, so we had e of x was just equal to 0.3, if you remember, and e of y was equal to 0.5. So we can just use all this together then. So we have e of, this simplifies, using this formula from above, it's the sum over x, sum over y, every possible value y takes, and x. So this is going to get x minus 0.3 and y minus 0.5, because this is just plugging in 0.3 here and 0.5 there, times probability x takes these two particular values. And there's just 4 possibilities. So again, we can work this out. We're going to get, firstly start, x equals 0, y equals 0. Well, in this case, we get minus 0.3 times minus 0.5, and the probability that x equals 0 and y equals 0 is 0.4. And we can go on like this. Next part will be y equals 0, x equals 1. Well, this will give us then 1 minus 0.3 multiplied by, well, 0 minus 0.5 will be minus 0.5. This occurs with probability 0.1. And so on. And we can go down and we can find, well, what's the next outcome? Y equals 1 will give us 1 minus 0.5 here. And if x equals 0, we will get minus 0.3. This occurs with probability 0.3. And finally then, the last outcome, y equals 1 and x equals 1, will give us 1 minus 0.3 and 1 minus 0.5. This occurs with probability 0.2. So if you add these all together, will give us the covariance of x and y. So we can see that we can work out the average of any function of x and y. Once we have the distribution function, then we just apply the formula from above. So finally then we can look at what's known as a conditional distribution. A conditional distribution just gives us a probability that some random variable takes on different values, given that some other variable took on some other particular value. So it's a probability that an event happened conditional upon something else already occurring first. So the definition, we'll just focus on the density of y given x. We can do the exact same thing in reverse for x given y. Well, the definition is, it's a probability y takes some particular outcome, given that x took some particular outcome. This just says, what's the probability y equals little y, given that x took on value little x. And we use this notation here, f of y given x. So for example, we may want to know, let's just say y was the event that someone has a job, and x could be the event that somebody had a degree or not. So we may want to look at, well, what's the probability that, say, y equaled 1, for example, that they had a job, given that they had a degree, for example. Okay, so we're looking at the probability some event occurs, given that some other events already occurred. So this is often very useful for in economics and finance we want to predict. So how can we work this out? Well, using the running example from before, we have the joint density given beneath. Well, if x equals 1 occurs, then we can rule out the case that obviously that means x equals 1 is out. So this just means we know that these already didn't occur. We know now we're in this world here where x equals 1. So this just this reduces the sample space. We now know that x equals 1 occurred, so we can then from here work out, well, what's the likeliness of y equals 1 and x equals 1? Well, we can see here that when in the world where x equaled 1, there is twice as much chance that x equaled 1 than x equaled 0. So we should expect to find that this would equal a third. Looking here, as I said again, we now know these only two events can occur now. Y equals 0 or y equals 1, because we know that x equals 1 occurred. And we can see the relative frequency here. Well, we can see that y equals 1 in this world occurs twice as often as y equals 0, which would say that the probability y equals 1 was 2/3. Okay, we can also see then this would also follow by Bayes' rule. This is just equal to, well, the probability x equals 1 and y equals 1 divided by the probability that x equals 1. Well, this is just 0.2, and the probability x equals 1, well, this was 0.3, the two added together, which would give us 2/3. So this just actually shows where Bayes' theorem comes from. We can see we can work this out by Bayes' rule, or we can see that within the world when x equals 1, that y equals 1 twice as often as x equals 0, which would say that the probability was 2/3, and so on.